Hi. First, I want to thank the organizers. This is really an amazing opportunity. So the work was done together with Zelza Bayad, David Kammer, Gil Cohen, and of course, Jean-Francois Molinari's group, who run amazing numerical simulations. We got a lot of help from Mukhtar Adabedia, setting us in the correct path, and Ran Buchbinder for continuous support. And of course, Jay is the mastermind behind. I can tell a lot of funny stories about him, but I prefer to do that in private if you ask me. Let me just say that I can't imagine a better advisor for myself.
That's a sad story.
So at the lab, we run a textbook friction experiment. We take two blocks, press them together, and then shear the system up to the point that it goes from stick to slip. Okay? And what I show you during the talk that the underlying physics of this process are actually intimately related to the physics of propagating cracks. So there is a very vast community that is interested in friction, starting from nanometric scale. I guess we'll hear about that tomorrow. Up to geophysical scales, as was already discussed. And we suggest, or people suggest, that laboratory experiments can provide a toy model for earthquakes, in a sense that the two blocks might mimic the two tectonic plates. The frictional interface might represent the natural fault. Okay? So the first thing to understand or to realize is that when the two blocks are pressed, the real area of contact, A, is much smaller than the nominal one, and this is due to the roughness of the frictional interface. So when the shear force is applied at the transition from stick to slip, those contacts are being broken, which results in a reduction of the real area of contact. At the lab, we are able to directly visualize the real area of contact. This is done by a method of total internal reflection. So the plates, the blocks are transparent. When the incident light above the critical angle is reflected, when the top block is pressed at the contacts, the light is being transmitted. We collect this light by using fast cameras, more than 500,000 frames per second. And the measured intensity is just proportional to the real area of contact. So this method goes back to Shmuel's PhD with Jay. Since, one note is that the width of the frictional interface is much smaller than any other dimensions of the system. We therefore integrate the intensity along the width, and therefore treat our interface as a line within two-dimensional system. Since then, Oded supplemented the contact area measurements with measurements of strain, and we then developed it a bit. So right now, we are able to measure the complete 2D strain tensor at about 20 locations along the frictional interface at high rates of 1 million samples per second. And the measured strains can be related to the stresses just by using the Hooke's law. So I'll start with a typical example of a propagating rupture front. So the x-axis is just the coordinate along the frictional interface. The y-axis is time. Colors are the contact area. Each horizontal line is just a snapshot of the real area of contact across the entire interface. And what you see is that the rupture nucleates on the left, it propagates to the right, it accelerates. At the wake, the contact area is being reduced, and macroscopic relative motion of the two blocks occurs only once the rupture has traversed the entire frictional interface. So this is essentially our first clue that the onset of frictional motion should be considered as a dynamic fracture problem. So during the rest of the talk, I'll compare results to fracture mechanics, so extremely short review. So we take a linear elastic material, we apply shear, we introduce a crack, propagates to the right with a velocity, and linear elasticity predicts a square root singularity of all the stress components at the crack tip. So essentially, this square root singularity is the definition of brittle fracture. Now, the only sink of energy is at the crack tip. Therefore, we have also an energy balance, which means that the energy flux to the crack tip should be balanced by dissipation there. And finally, I want to note an important velocity scale. This is the Rayleigh wave speed, which serves as a classical limiting velocity for cracks. And during the talk, I'll refer to each one of these points. So we would like now to characterize propagating ruptures. So we start with a slow example. On the left, I'm plotting a snapshot of the measured shear. X tip is the rupture tip position. So the measurement is here. For negative x minus x tip, it's just the region where the contact area is already reduced. The rupture propagates to the right with the local rupture front velocity of 4% of the Rayleigh wave speed. And if we repeat the same procedure for different rupture tip locations, which correspond to different velocities, we observe that the spatial profiles of strain collapse to a single functional form. And actually the same goes for the XX and the YY component of the strain tensor, okay? So we would like now to compare our measurements to the prediction of fracture mechanics. Let me remind you that our strain gauges are located slightly above the frictional interface. So the rupture propagates, both R and theta are being varied. This is the square root singular prediction. This is a snapshot of the singular prediction. This time y-axis is just the vertical coordinate. This is the crack. In order to compare our measurements on the left to the predictions on the right, we should consider the predictions along the black dashed line, which corresponds to the measurement location. And we have only one free parameter, K, the stress intensity factor here. All else is directly measured. And actually, one free parameter fits all of the strain components. Fracture mechanics relates the stress intensity factor K to the fracture energy gamma. Gamma is just the energy to break a unit area of contact, and which results in a value about 1 joule per square meter. Okay, so we've discussed slow ruptures. Those propagate at small fraction of the Rayleigh wave speed. What about faster ruptures? This is an example of 96% of a Rayleigh wave speed. Again, we see an excellent agreement at high velocities. This time we have no additional free parameters. We just use the same fracture energy from before. Would like to make a point that the strong oscillations that we see are actually due to the violent angular behavior of the solution, okay? The same oscillations also appear at the shear component. However, a closer look shows that the square root singular term apparently fails to describe our measurements for the shear component just ahead of the rupture. So during the next slides, I'll explain why, and I'll try to convince you that it is actually a bit interesting. So in order to understand this apparent discrepancy, we separated into two parts. So first, as indicated by the red double arrow, far ahead of the rupture tip, it's actually very intuitive. As we know, the square root singular term should be dominant only close to the rupture tip. Therefore, this is quite obvious. Okay, but as we approach the rupture tip location, we observe a prominent shear peak, which is actually absent in the square root singular term. And I'm superimposing a measurement at a later time, T2. And I want you to know that this prominent shear peak actually progressively distance itself from the rupture tip. So what we did, we followed the position of this shear peak. These measurements are superimposed on the contact area measurements. And we see that this shear peak propagates faster than the rupture in the region where the contact area is not broken. Its velocity is the shear wave speed. And the backward extrapolation reveals that its origin somewhere at the late stages of the acceleration. Okay, so this gives us quite a lot of intuition. So what we see is that the rupture that nucleates and that accelerates, it's a non-steady process, which results in strong stress wave radiation. So we would like now to understand this form of radiation in the framework of fracture mechanics. But to do that, it is quite complicated. You need to solve the complete boundary value problem. It's really intimidating. And there are several simple problems that appear in the literature. So for example, Broberg considered at the 60s the following one. There is an infinite medium under shear. At t equals 0, a crack is born and propagates at both directions, this time at constant velocity. So there are no additional length scales at the problem. So, so it suggests we may look for self-similar solution. Actually, Broberg had used the self-similar ansatz and was able to solve the stresses within the material. So for example, I'm plotting the shear stress along the crack line. This is the crack tip. This is the square root, the universal square root singularity. And just ahead of the singularity, there is a prominent shear peak that I guess you see where I'm going with that. Before that, I just want to know this is quite a simple problem, or too simple. It results in fractional energy, which grows linearly with propagation distance, which is not observed in our experiments, but I don't have time to go into the details. So blue are strain measurements, black the square root singular term, and red is the complete self-similar solution of the problem. So it's identical for the XX and YY component with the singular term, and it obviously fits our measurements ahead of the crack tip. Again, we have a lot of intuition. This is a complete boundary value problem, therefore it captures the initial pre-shear stress, meaning that we need to take into account non-singular contributions, and of course it captures the prominent shear peak. So let me summarize quickly the physical picture. The rupture nucleates on the left, it accelerates, it generates a lot of energy which goes at the shear wave speed, okay? So why is it actually interesting? I think I had a spoiler from Mike Marder. Up to now, we've considered the sub-Rayleigh regime, where ruptures propagate below the Rayleigh wave speed. There is another family of solutions above the shear wave speed, and there was predicted at the 70s a forbidden range of velocities, although Mike Marder has challenged this, but let's put it aside. And the paradox was how the supershear ruptures can be excited if the rupture cannot continuously overcome the forbidden range, okay? I'm exposing the rest of the experiment, zooming in this region. I want you to know that out of the blue, at this point of time, a new rupture is nucleated, which propagates above the shear wave speed. So our synchronized measurements of the contact area and the shear stress reveal that this super shear rupture was triggered by the arrival of the shear peak. So again, what's the story here? The rupture nucleates, accelerates, radiates a lot of stress energy that propagates above the shear, at the shear wave speed. If the radiated energy is strong enough, it can break the material ahead of the crack and nucleate a secondary rupture just above the supershear region. So this mechanism was suggested by Borage and Andrews at the 70s, since was extensively studied by many. So quick summary, up to now we've discussed about the singular fields within the vicinity of the rupture tip. And this is the normalized rupture velocity. This is the crack length, and we've discussed slow ruptures that propagate at a small fraction of the Rayleigh wave speed. And we've discussed rapid ruptures that accelerate to the Rayleigh wave speed. And the question is, okay, but what determines rupture velocity? What determines CF of L, or in the jargon of this community, what determines the equation of motion of these frictional rupture fronts? So in the fracture mechanics framework, it's given by, the answer is given by an energy balance. So there is a long history of people who contributed it. We follow, I think the last part was completed by a seminal work by a friend at the 70s. So the equation of motion goes like that. The energy flux to the rupture tip should be balanced by the fracture energy. So if you can calculate the energy flux there, you implicitly get the rupture velocity with respect to the crack length. So I've convinced you that we have the right hand of the equation because we know fracture energy. And we follow friend to calculate G. So to do that, I want to define a new quantity, which is the stress drop. It's just the initial stress with respect to the residual value. So it's just the amount of shear you apply. And what a friend was able to show that G in fact can be calculated. There are several restrictions, but never mind. And more importantly, he showed that it can be separated to two parts. The static part, the elastic energy being released, which depends only on the crack length and the applied loading, and the dynamic correction. So in principle, we know all the ingredients. So does it work? These are the three rupture events we've discussed. These are the accompanying shear stresses from which we can calculate the elastic energy being released. I'm plotting elastic energy being released divided by the fracture energy with respect to the crack length. And as the equation of motion suggests, instead of plotting the velocity with respect to the crack length, I'm plotting the velocity with respect to gs over gamma by that measurement. The black line is the fracture mechanics prediction. And just to convince you more, I'm adding more examples which show that all rupture velocity profiles collapse to the same single LEFM predicted curve, which means just that fracture mechanics describe wholly the equation of motion.
Do you have any friction at the tail for your fits?
The stress drop defined between the initial impulse stress with respect to the residual value. Following Rice's work at 68, because of the linearity of the equations, you can essentially subtract the residual value at the tail. So this is the mapping, the direct mapping between the frictional rupture fronts to the free crack face in brittle cracks.
But the residual, you subtract what you measure as the sliding velocity of the tail?
Yes.
Or you fit it?
No, we measure it. I measure the pre-stress, I know the residual stress, I subtract it, and I define the stress drop. And all calculations are based to this stress drop, okay? So it looks like a magic, but it is actually easy to understand, right? So slow ruptures propagate under very low shear stress, which results in elastic energy being released, goes entirely to dissipation. In case of an excess of elastic energy, where the GS is much larger than the fracture energy, the ruptures have to pay with the kinetic energy, and therefore they accelerate. So, quick summary. So we are doing a friction experiment, really typical experiment. We observe frictional rupture fronts, and what I've showed you that these are mathematically identical to propagating brittle cracks. So we showed that the fields at the rupture tip are described by singular prediction of fracture mechanics. We've talked about stress wave radiation due to rapidly accelerating ruptures that again described by fracture mechanics. And then we used the energy balance given by fracture mechanics to describe the equation of motion of these ruptures. And there are a lot of open questions. So for example, we don't really understand how these singular fields are regularized. We have no clue about what happens the nucleation. There are some interesting questions about supershear, and Adar will tell you about what happens within the similar material. Thank you very much.
No, just a curiosity, because your strain gauges are at certain distances of the surface where the crack propagates. So why in the data analysis you never consider a time of flight between between the position of the tip and your signal? I mean,
yeah.
I was surprised that indeed it seems everything is stationary.
Yes. So the stationary is the crucial point. So essentially, we believe that on these length scales, it can be considered. The acceleration is slow enough in order to all the fields up to 3 millimeters to adjust, and we see just locally a the stationary solution. So in fact, also the equation of motion by Friend was built upon superposition of stationary solution. Mathematically, it can be allowed if always you go close enough to the crack tip. Even at high velocity, high acceleration, you can go even closer to the crack tip where you will have the K dominance, which is always stationary solution. In practice, it works.
How do you prepare the surfaces? They seem to be very well bonded, and I wonder if you clean them, and what happens if you contaminate them or lubricate them?
Yes, this is very important. We clean the interfaces by some protocol that we try to repeat. it doesn't always work, but we didn't study it system.
Is it organic solvents? Is it
We use a bit of detergent and then how it's called, isopropanol, wait for an hour or two, and then do. We intend, or in the future, hopefully change the roughness of the interface, for example. Regarding lubrication, tomorrow Elsa will tell you what happens. I don't want to give spoilers.
Last question.
You studied, because of dimension, etc., essentially just a rupture of a very small displacement moving along the interface. So basically you deal with the fracturing at the rupture front. What happens if this was a case of a large shear event, let's say during an earthquake, in which the rupture front is just a small portion with respect to the backside of the fault that continue to slip for a meter or two.
So one second. So I didn't put any restrictions about the amount of slip at the tail. So this predicts a square root displacement at the tail, and if your system large enough, it will go to infinity in a sense. So we just stop our experiments when the rupture reaches the end of the sample, and their boundary effects will enter. But if the system would multiply it by 1,000, we will get much larger displacements, if anything else doesn't break.
But what about, you're looking here, okay, do you think that the width of this picture that you have here in terms of the rupture condition, the rupture front condition, will be just widen?
So I think if I understand the question is, let's say the interface will be 10 meter and 10 meter in either side, how well we see the correspondence back weight, right? So assuming nothing breaks within the theory, it's only a question when the non-singular contribution will become important. This is the square root singular term only important at the rupture tail. When the non-singular contribution will kick in, it's question that I never seen an answer, concrete answer for that.
Well, there isn't any.
No, not in
Yeah.
this term. There are solutions, but not in the rupture.
Yes, I'm afraid we would need to.
Maybe this is brief, maybe not, but you can show how important stress drop is and how it controls whether things go fast or slow. So what controls the stress drop?
I guess we can talk about that later, but this is the most important question of the talk that I didn't discuss, and it comes the question about nucleation. So essentially, we have different stress drops, which corresponds basically to different friction coefficient, and I never told you why there is a rupture that propagates at low stress drop, and then what we do, we shear the stem after we did some prayer at the morning, and if the rupture wants to nucleate, it nucleates at a small amount of shear stress, and if it's a bad day, it will nucleate at a larger stress drop, and we get. So we only collect the results and analyze. We don't understand nucleation, which is the answer to this.
But the humidity.
What?
Humidity is controlled?
Humidity is not controlled, but within the same day, within the same hour, I can just slightly readjust the blocks, and I can get totally new results. So in a sense, it's a bad experiment in this sense.